There we go. Yes, success. We can go now.
So please start. So the title of your talk is written over there, right? Yeah. Everybody can read it, so you can start.
Yeah, that's the title of the talk. Yeah, so thank you all for turning up. I know there are lots of talks to go to, and only so much time. Thanks to the Leary Human Trust and to the Newton Institute for sponsoring me in some way. And yeah, as I say, thanks for all for coming. Co-authors. Yeah. So the main thing. I often call this talk Uncountably Many Groups of Type FP, because that's the main point. We construct uncountably many groups of type FP. And I heard that question from Chuck Miller in a conversation with Peter Kropholler, Chuck Miller, Robert Kropholler, and Martin Bridson. And Peter and Martin and I said we were going to try and work on this question together afterwards. And I know Martin Bridson was keen to try and construct uncountably many groups of type FP without using the Bestvina-Brady mechanisms, and then that giving you proof that there were groups of type FP that weren't finally presented because we'd constructed too many of them. Yes. Anyway, so at some point I had a good idea and I wrote to Peter and Martin about it, and they didn't reply for a few weeks. So in the end, I'd done so much of it by the time they replied that I cut them out. So okay, I don't have any co-authors except there's a bit about quasi-isometry. No, they very kindly agreed that, and that's joint with Ignat Soroko, who's a student of Brady, just finishing. He's looking for a job, but he only wants to be in Texas, I think. And Robert.
Is he paying for him that much? He only wants to be in Texas.
No, I'm not sure.
Oh,
He's got some complicated family reasons to need to be in some parts of the US.
Okay.
Yeah. Okay, so I probably won't get time to talk about this bit anyway. Shall we say what the finiteness conditions are? So I've got a discrete group G, so G is type F. That means G has a finite KG1. Finite KG1. And I think I want instead to talk about the universal cover of this. So it's if and only if G acts freely cellularly properly discontinuously, if that's not implied by cellularly, on contractible complex.
So you don't need co-compactor.
Well, sorry, yes, of course. Freely, co-compactly. Thank you.
Okay,
Yeah, sorry.
But it wasn't me this time, so excellent.
Freely co-compact. Actually, I'm going to erase that and put co-compactly in properly. On a contractible complex. Okay, so I guess you've all seen this. There's also Fn, so every group is F0, F1 is the same as finitely generated, F2 is the same as finitely presented, and there are higher and higher conditions that are less than this. So then there's the one that Bestvina and Brady introduced, type FH, and this is not fixed points on Hilbert spaces. This is sort of homology version of this. If and only if G acts freely co-compactly properly discontinuously cellularly. See, I shouldn't have written this bit in, then I could have just put ditto marks all the way across on an acyclic. Right, so all we've changed is
Acyclic is trivial homology in every.
trivial, yeah, same homology as a point. Yeah. Yeah. So all we've changed is contractible has changed to acyclic. Yeah. So obviously type F implies type FH. And then there's things you can do when you take the cellular chain complex. So G is FL. Oh, and then FHN. In F, I didn't really tell you what F2 meant. F2, you could say acts freely or compactly, probably discontinuously on cell complex with trivial fundamental group, so one connected. So F2 would be the same as all of this, but with one connected instead of contractible. F3 is the same as all of this with two connected instead of contractible. And so there's FHN as well. And that's the same as this with n-1 acyclic. So it's homology groups up to the n, up to and including the n-1 first, the same as those who are one. Okay, so FL, if and only if Z has Z, we're in not Z, has free a finite, yeah, a resolution of finite length by finitely generated free ZG modules. Okay, and if you think about it, the cellular chain complex of the cell complex that witnessed FH is a, I mean, it's because saying that this is acyclic is the same as saying that the chain complex is exact, except you need to put a Z at the end to make it exact. The Z from the zeroth homology group. Yeah. Okay, and then we can forget that frees are free, they're just projective. So Z has a resolution of finite length by finitely generated projective ZG modules.
So that's different usually, right?
Well, yes and no. And there is no known group that is FP but not FL. So I mean the issue is oh well, you can do all of this over more general rings, right? If you do it over the rationals, any non-trivial finite group is FP over the rationals, but amongst finite groups, only the trivial group is FL over the rationals. That's not hard to see. Yeah. So there are more general situations in which these things differ, but there's no known. Oh, so a group that has any of these four properties that is torsion free, and there's no known projective module for ZG when G is torsion free that isn't stably free. So, yeah, there's no known difference between these two. There's no known difference between any of these three, actually. Yeah, I mean, there's no known difference between any of these three. This implies this, implies this, implies this. Yeah. However, there is a known difference between F and all the others, and that was what Bestvina and Brady did. So that's the Okay, so the Bestvina-Brady construction.
Yeah, I'm very sorry. Can I?
Yeah.
Are there any other situations in which things are known? Did Wall prove that some of these things are the same some of the time?
You're thinking of the wall obstruction or
Right.
something,
I
the
don't
wall
know what I'm thinking of,
finiteness
but it would
obstruction.
really help if you could tell me
I'm
what
not
I'm
sure.
saying.
So the thing is, the difference between FP and FL is measured by an element of reduced K0 of ZG. So you take K0 of ZG and you factor out by the subgroup generated by the finitely generated free modules. And then if you take any resolution, you can take the alternating sum of the modules in it. That is an element of K0.
Right.
And the group is FL if and only if that element is 0 in this, is equal to the free module in K0. So there are some quite exotic examples. I could plug my own exotic example at this point. If you take I used to do a talk called the prism and the Möbius strip. If you take the index 2 subgroup of, that's not quite right, is it? Take an equilateral triangle and the reflections in the 5 sides of this prism. Take the orientable index 2 subgroup of that. Right, so we've got an infinite group, a 3-dimensional crystallographic group. That group is FPQ, so it's FP over the rationals. It's got torsion, so it won't be any of these over the integers. It's FLC, and in fact it doesn't really need to be C, we just need a primitive cube root of 1, but it's not FLQ. Right, so I mean it's not a complicated calculation, but whereas if you think about it, FH can't see field extensions. If you've got if you've actually got a cell complex and it's CA cyclic, then it's also QA cyclic, right? So this gives you an example of a field for which FH over that field is not the same as FL. Yeah, because this group can't be FHC because it's FHC if and only if it's FHQ. Right. Okay, so yeah, I mean, if you get to bigger rings, there are differences, but I mean, essentially for today's purposes, these are all the same, and nobody knows that they're different over Z. So, okay, so what was the Bestvina-Brady construction? Right, they take a finite. I'm going to have to erase this again, I guess. So they take L, a finite flag complex, so for example, the barycentric subdivision of any finite simplicial complex. Yeah, so what's a flag complex? I like Warren Dick's definition. Every non-simplex contains a non-edge. Yeah, that's so equivalently, whenever you see the one skeleton of a simplex, the whole simplex is there. Yeah, so it's a simplicial complex, but yeah, has that property. So they associate to this a group which everybody calls BBL. And it's actually the kernel of a map from the right-angled Artin group on L to Z.
The obvious map.
Sorry?
The obvious map.
Yeah, okay. Kernel of the obvious map from the right-angled Artin group to Z. In such a way that BBL is finitely generated if and only if L is connected. BBL is finitely presented if and only if L is non-connected. So, connected and has trivial fundamental group. we could say BBL is type F. Yeah, let's put it down here. F, if and only if L is contractible, BBL is FH, if and only if FP. So, I mean, you know, you usually state it with FP. If and only if FH, if and only if L is acyclic. Okay, so this gave the first examples to show there was any difference here. So these groups, if you take an acyclic but not contractible flag complex, then this group is type FH, type FL, type FP, but it's not type F because it's not finitely presented. Right? So this was the first examples of groups that were FP, usually say FP, but in fact they showed they were FP by showing a stronger condition FH. So these are first examples of groups that were FP but not finitely presented.
Is that the famous paper where they use Morse theory?
Yeah, that's the one. Yeah, the famous. Yeah, I think there's only one Bestvina-Brady paper. That's got 150 citations or something. Yeah, that's the one. And yeah. Okay, so there are only countably many of these, and the right-angled Artin group, I haven't said anything about that, I hope to say something about that, is of type F. So every one of these is a subgroup of a finitely presented group. They're also finitely generated, of course, because I didn't say that, but finitely generated is equivalent to FH1, FL1, FP1. They're all equivalent, right? So all of these groups are finitely generated. Well, assuming L's, I'm not going to think about L not being connected. Yeah, there's only countably many of these Bestvina-Brady groups, and they all occur as subgroups of groups of type F. So that left a question: can there be more than countably many groups of type FP? Do they all embed in finitely presented groups, even groups of type F, if you prefer? Okay, so those are the questions that this new thing answers. Yeah, I'm really excited about it, but I keep getting it sent back to me from journals that don't want it, so maybe it's not as exciting as I think. I don't know. So the new process, we start with L, a connected finite flag complex. And let's say with universal cover, L tilde, right? So I'm mentioning that as well, and S, a subset of Z, right? So I've still only got countably many finite flag complexes, but I've got lots of subsets of Z. That's going to be where I'm going to get extra groups from. And to this, I associate a group GLS, and they're all going to be finitely generated. L's a subscript, so you can't get it confused with the general linear group over a ring S or something. Yeah, S is for subset, finitely generated. And the functoriality is, they essentially, for fixed L, they all have the same generating set, more or less. I mean, if S is contained in T, then we have a map from GLS, a surjection from GLS onto GLT. And Okay, I didn't assume that the fundamental group was non-trivial. Let's tell you the main. Yeah. So for fixed L, the following are equivalent. For all S containing Z, GLS is type FP or type FH. Oh, let's say, yeah, for all S containing Z, GLS is FH. And thirdly, L and L tilde are both acyclic. Right, so another way to say that is that L is acyclic and aspherical. So L is a KG1 for some other group G that is an acyclic group. Yeah? So, I mean, the thing is there are examples of L's like this. There are examples of L's like this. Now you can say other things about if S is finite or if S is co-finite, but essentially if you have this for one infinite, co-infinite, and you have some condition on L, then that implies you have this for all S. Yeah, so, but I mean, yeah, this is the simple statement. You can make a statement with FPN, it's just what you'd think it is. This is FPN if and only if this is FHN, if and only if these are both n-1 acyclic. So have the same homology groups up to and including degree n-1. Right, I haven't assumed that the fundamental group was non-trivial yet. If the fundamental group is trivial, then they're all just the same group. So yeah, we don't want to think about that case. Right, so okay, so if pi1L is not trivial, there exist uncountably many isomorphic. For fixed L. Yeah, fix L. Right, we fix L and vary S. So if pi1L is not trivial, there exist uncountably many isomorphism types of GLS as S varies. Yeah. And the result with Ignat Soroko and Robert Kropholler, uncountably many quasi-isometry. Right, so as I say, I probably won't get time to talk about this, but you know, you can pick 2 to the LF0 different sets S such that no 2 of the Cayley graphs of these are such that no 2 of the Cayley graphs are quasi-isometric to each other. What else can we say? If this, then, so I'm going to assume that pi1L is non-trivial. In this case, GLS is finitely presented if and only if S is finite, and GLS is embeds in a finitely presented if and only if S is recursively enumerable. So, I mean, this is what Hickman did in the 60s. Yeah? So, if the point is you're going to get a presentation for GLS which depends on S. They're related are somehow indexed by S. And as long as S is recursively enumerable, then the Hickman embedding theorem applies. But the converse is true too. Yeah, so this is isomorphic to a subgroup of finite Brentano group if and only if there's an algorithm to generate S. I guess that's about it for the original theorem. There's a couple of sort of corollaries that I always like to mention. Yeah, you can do a Davis trick. So Mike Davis used the original Bestvina-Brady FP but not finitely presented groups to create a non-finitely presented Poincare duality group. So a group that's, in fact, the way his groups work, they act freely co-compactly on an acyclic manifold. Whereas a genuine fundamental group of a closed manifold would act freely co-compactly on a contractible manifold. Oh, freely co-compactly probably, you know, all the adjectives. Yeah. So you do the same thing here. So I guess there exist. Oh, yeah, when I say uncountably many, it's always 2 to the LF0. Nobody likes the way I write Aleph, so I'm going to try and avoid writing it on the board. There exist uncountably many. No, hang on. For all n greater than or equal to 4, there exists a spherical n-manifold. And then with an uncountable collection of regular covers, regular acyclic covers, of course. Yeah, sorry, regular acyclic covers with non-isomorphic groups of depth transformations. With non-isomorphic, and we're pretty sure about non-QI, but that's still work in progress. Right, so quasi-isometric. Yeah, I'm yeah, okay, we haven't, groups of, well, you know, the group of depth transformations. Right, so each one of these groups is a not necessarily finitely presented, and usually not, Poincare duality group of dimension n. Yeah, so for each n greater, so yeah, and when you first heard about Mike's example, you thought, oh, I'm glad I don't meet many of them. But in fact, there are more of them than there are normal Poincare duality groups. So only countably many normal Poincare duality groups. And the other thing that I want to write up as a, it's sort of not completely just a corollary. Every countable group embeds in a group of type F2. Sorry, FP2. No, F2 it can't be right. Right, so this is an analog of the Higman embedding theorem. Higman embedding theorem tells you when, well, hang on. No, there's the Higman-Neumann embedding theorem. Every countable group embeds in a 2-generated group. And then there's the Higman embedding theorem, which tells you which finitely generated groups embed in finitely presented groups. Such a thing happens if and only if there's a recursively enumerable presentation. So there's an algorithm to spit out the relations. Yeah. So once you know that FP2, subgroups of FP2 might be different from subgroups of finitely presented, you have to say, well, which side does it fall? Or is there some third class between all countable? Well, yeah, so the thing is that the statement that Higman embedding theorem is more Yeah, it's not true that a countable group embeds in a finitely presented group if and only if it's recursively presented. The problem is there are things like, so take the direct sum of cyclic p for all p. That's recursively presented, so it embeds in a finitely presented group. It has lots of non-recursively presented subgroups. Direct sum over all p in some non-recursive set of primes. Yeah, so that's why the Higman embedding theorem is always a statement about finitely generated groups, but really it sort of characterizes, says a group embeds in a finitely presented group if and only if it embeds in a recursively presented group. Okay. Yeah. So anyway, once you know that there's a difference between FP2 and finitely presented, you have to ask a question like this. Which side does it fall? Is there some third class of groups intermediate between all groups and recursively? But no, in fact, the statement sounds more like the Higman-Neumann embedding theorem, but the proof is a lot more like the Higman embedding theorem. Right? I don't know if I should try to say anything about. I'd like to give a talk about this, but I always want. I think the sort of geometry and the branch covers is what I should talk about today. So, oh yeah, but I like to write this on the board because it's my counterexample to Gromov's assertion that a statement that's true for all countable groups is trivial. And if you please try and find a proof of this that doesn't go via Bestvina-Brady theory. Yeah, because the thing is, this would answer Martin's question. Martin wanted to establish that FP2 wasn't the same as finitely presented by exhibiting uncountably many. Well, if you can do this, if there's an elementary proof of this, you can answer that question. Yeah. So, I'm definitely relying on understanding enough of the proof of Higman's theorem to see what to change and all the Bestvina-Brady stuff to get some groups that. Okay, so I guess I want to say a tiny bit about the proof of the Bestvina-Brady theorem, and then a sort of background theorem to where all of this comes from. How long should I spend on the Salvetti complex of a right-angled Artin group? So not long, but epsilon.
Cool.
Yeah.
Let epsilon tend to 0.
Oh, yeah. Okay. Everybody is everybody.
Definitions.
Well, maybe just to establish notation. So, L a finite flag complex doesn't have to be finite actually, but let's keep it finite for now. So, TL, the Salvetti complex. It's a subcomplex of the product over V a vertex of L of a circle TV. So each TV is a copy of S1. And I want to make TV into a cube complex with one vertex at the identity and one edge. So yeah, I'm going to think of this as a multiplicative group, and or we could think of it as R mod Z, and I'm making it into a cube complex with one cube and one 0 cube at the identity. Right, so T sigma is the direct product of V a vertex of sigma TV. I want to view it as as inside this, so I'm going to say it's direct sum product. It's that crossed with W not a vertex of sigma, but W a vertex of L, and then just the point. I don't know, whatever that point's called. Point sub V.
W.
Point sub W, yes.
Yeah.
Okay, and then TL equals the union sigma, a simplex of L of T sigma.
It's just a bunch of tori.
Yeah, bunch of tori glued together. Why did I spend so long on this? There's a map from TL to the circle. Let's call it T of a point, the circle, which is just the group operation on, multiply together all the different coordinates. Or if it's R mod Z, add them all together. Yeah, so you've got, you can take, an element here is just an element of the torus, the big torus, but its support is contained in some simplex. So then you can use the group operation on the circle to add all of the coordinates, and that's this map. I haven't given a name. Okay. Got H or something. Right, so we've got TL goes to the circle, U1 or S1 or whatever, and we can take the universal cover there. Oh, yeah, and the other thing I should say, that the map on fundamental groups induced by this, that's the homomorphism that Bestvina and Brady take. Oh, yeah, because the fundamental group of TL is the right-angled Artin group, and TL is KAL1. So, what relations do we, sorry, I didn't say any of this, did I? You have a generator for each vertex, the generator being go around the circle TV in the positive direction. Whenever two vertices are joined by an edge, you've got a two torus telling you that those two generators commute. Right, and that's all the relations you've got. So the right-angled Artin group, the generators are the vertices of L, and the relations are the ends of each edge commute. Sorry, I should have said that already. Okay, so we've got that map there, and we take the pullback so that just the cover corresponding to this. I haven't drawn the picture that I usually draw. Let's draw, we'll draw the case when L is just a single interval. L is 2 points. So then we have so if I take L to be 2 points, TL is a two torus, and I want the map, I want the infinite cyclic cover of a two torus where all of the edges point up and they all go one up each time. Right, that's the Bestvina-Brady picture. Right, and so say these are my, so here's L. It's got two vertices A and B. The Bestvina-Brady homomorphism, we send A to 1, we send B to 1 in Z. So the A edges and the B edges both point upwards. This is on the B edge and that's on the A edge. Okay, so that's the infinite cyclic cover. It's got a map to R, and each vertex goes to an integer. And each edge goes to an interval of length 1. Yeah. Okay, so the Bestvina-Brady group is the fundamental group of this thing, the infinite cylinder. So if you like, you can think of it as the group of deck transformations of the universal cover of covering map of this. Right, so okay, so then the sort of subsidiary theorem is for all S containing Z. Oh yeah, sorry, I should say, so this is a copy of R here. This is TL tilde, sorry. I'm not sure I should use the tilde there. I was using tilde for universal covers before. Let's call it hat. Something. It's some sort of cover of TL. And the vertices are in one-to-one correspondence with Z. Yeah, so that's n minus 1, n minus 2, etc. The vertices are, the original space had one vertex. This space has vertices indexed by Z. Yeah, now there's one more thing I wanted to say. What's the link in this space? Yeah. Right, sorry. If you look at the link just in this circle, so this is the circle TV, the link of this vertex is two vertices. It's got a vertex V plus and a vertex V minus. Yeah? And whenever you have a simplex in L, a one simplex in L gives you a sort of square here. So we've got the link of this vertex, it's got a vertex A plus, a vertex B plus, a vertex B minus, and a vertex A minus. So there are four vertices in this link. And A to the epsilon is joined to B to the epsilon dashed for each choice of epsilon and epsilon dash. So vertices with a sign are joined if and only if the vertices without sign were joined in L. Right, so vertex link is S of L, sphericalization of L. So it has twice as many vertices, so vertex set, the vertex set of this, that's each vertex link in TL or in TL tilde. Yeah? So it's got twice as many vertices as L, it's got 4 times as many edges as L, because an edge can end in a plus or minus vertex at each end. It's got 8 times as many two simplices as L, because you've got 3 choices of sign. What does it look like in 3 dimensions? It's like an octahedral. It's the boundary of an octahedron. Yeah? So I call that A plus and A minus. That one B plus and that one B minus. That one C plus and that one C minus. Okay, so it's an octahedron. I should really have drawn it this way because the plus with the plus simplex at the top and the bottom simplex at the bottom. Yeah. Okay, so this is the sort of operation you do. So essentially it's just L, but you replace each vertex with 2 vertices and replace each simplex is just a join of vertices, replace each vertex with 2 vertices, and then each simplex gets replaced with a join of whatever you replace its vertices with. Yeah.
So is it in particular true that the sphericalization of a simplex is always the octahedron of the
yes, of the relevant dimension. Yeah, yeah. So yeah, Boris Oakham likes to call it the octahedralization now instead. But I don't know. Yeah, I don't know. Sphericalization or octahedralization. Okay, so right, so the branch cover theorem is really what's behind most of this. So for all S contained in Z, there is a regular a cat zero cube complex. XL superscript S. Sorry, I did. No, I did. I did invent notation. Which is a regular branch covering. Of TL hat. Branched only at vertices, branched only at vertices, And then I have to tell you what the links of the vertices look like. And I want the link in.
So it's branched as the vertices will for the test?
I'm just about to tell you. It's branched at the ones not in S.
Not in S, okay.
I don't know. There are reasons for saying that. Yeah. It's equal to the sphericalization of L if V is in S, and it's the sphericalization of the universal cover of L if V is not in S. Right. Okay, so I can blow up the vertices that are not in S and leave the vertices that are in S intact. And the whole thing's a cat zero cube complex. I didn't say that the universal cover of TL is a cat zero cube complex because all these links are flag. Oh yeah, because SL is flag if and only if L is flag. Yeah, that's hard to see. Okay, so in fact this group GLS that I was talking about before is the group of deck transformations of this cover.
If the vertex is in S, it means the image of vertex in the line.
Yeah, the image of, yeah, let's say, yeah, exactly. I'm using this map H from here to here to identify the vertex set with, yeah. Okay, so, I mean, depending how well you know the Bestvina-Brady stuff, all the stuff about finiteness conditions works fairly similarly to what they do once you've got this result, right? So what's the idea? Why is so we've got this space XL that the Bestvina-Brady group acts freely on. We've also got the level set, so the inverse image of a point. We usually think about the inverse image of an integer. The inverse image of an integer is something that the Bestvina-Brady group acts co-compactly on, freely, co-compactly, nicely. So it doesn't act co-compactly on the whole thing because the quotient is this cylinder. But it does act co-compactly on this bit. So if we knew that the horizontal bit, that the inverse image of a point, was contractible, then we'd know that the group was type F. And if we knew that the inverse image of a point was acyclic, then we'd know that the group was type FH. Right? But then there's this Morse theory stuff, which tells you that to get, I don't know, let's erase all this stuff here. You don't need any of this. So the universal cover in this case is fairly simple. It's just the plane. It's the plane this way up, yeah. And the inverse image. Oh, see, I can't draw. Okay, you know what it should look like. You know what it should look like, yeah. It's the inverse image of a point.
Draw the horizontal first, yes.
Yeah, you need to do this as well, yes.
Is that cheating?
There you go. Yeah, perfect.
That's as long as I don't push it too far. That's sort of worked, hasn't it? Okay, the inverse image of this point, this vertex here, is this line. So say we didn't know that the kernel of the map from Z squared to Z was type F. Yeah, we could reason as follows. Well, this whole space is contractible. The group, the unknown group, which we probably our first years know is isomorphic to Z, but let's pretend we don't know. The unknown group acts freely co-compactly on the level set. Right, you make the level set by attaching cones on descending links. and cones on descending lengths for vertices that go upwards and cones on ascending lengths for vertices that go downwards to the level set. Right, so I attach cones on descending lengths for the vertices above, cones on ascending lengths for the vertices below. But hang on a minute, the ascending and descending links, the ascending link is just the thing generated by A plus and B plus. It's a copy of L. The descending link is the thing generated by A minus and B minus. It's another copy of L. That doesn't change anything because L is contractible. Since the whole space is contractible, therefore this thing was contractible. Right, so that's the Bestvina-Brady argument. And if you only want FH, you could have said everything I said with A cyclic instead. So the ascending and descending links are always copies of L. Oh, but for me, I can use this same function to make a Morse function on here. My ascending and descending links are either a copy of L or a copy of the universal cover of L, depending on which height I'm at. But as long as I know that both of these are acyclic, then I can run the same argument. And you know, there's a little bit of extra stuff you need to do, but the main extra thing is getting these branch covers. Should I say more about this, or should I? 5 minutes. I should probably say more about this rather than talking about embedding in FP2 groups, shouldn't I? And that's too much of a digression. Okay, so I'll keep that bit open. I won't erase this now. So there's a thing about cat zero spaces, which is a sort of general thing. So, let's say cube complexes just to be on the safe side, but I'm sure it's true in general. So if X is cat zero, we can identify a cat zero cube complex. Say a cat zero polyhedral complex will probably do. You can identify the vertex link with the sphere of small radius. You might even define the vertex link to be the sphere of small radius. So there's an inclusion from the vertex link to X minus V. And the proposition that probably everybody knows, it's surprisingly useful, the link is a deformation retract, strong deformation retract. Of X minus V. Yeah, we need to know things like this because we want more unwrapped links. Yeah? So the corollary is that the fundamental group of X minus V split surjects onto the fundamental group of the link. Right? Okay, so if I want to completely unwrap some vertices, if I want to make a branch cover where I've completely unwrapped some vertices, so I have the old links some places and the universal cover of the old links some other places, I can do that by just removing the vertices before I start and take the fundamental group of that, take the universal cover of that. That's a cube complex with some vertices missing, so you put the vertices back once you've done the universal covering thing, right? Okay, that's fine, except that we've created something where it's tilde of S of L, not S of L tilde. And that might not be what we want, right? So we need this. We don't want, this isn't always the universal cover of S of L. Right? If it is, then we've just done the right thing. We've created the space. So the other thing we need to know is that S of L tilde is the universal cover of S of L if, and I think this is if and only if, but I've never checked this, if L has no local cut points. No local cut points. Right, so surprisingly, this is a topological property of L, whether this holds. Right, so just to give you an example, how can this go wrong? Well, if L is an interval, if L is a single one simplex, S of L has some fundamental group that L didn't have, right? So there's a local cut point in the middle of an edge. The other example is if L is a bow tie. Yeah, if L is a bow tie, S of L is two spheres, two octahedra, joined at their north and south poles. Not a very good drawing, but we found some fundamental group that wasn't there yet again. It turns out that's the only thing that can happen. So the fundamental group of L is always a retract of the fundamental group of L, S of L. And as long as you don't have any local cut points, you get this. Right, so in the case when L has no local cut points, you can make this cover just by taking out the vertices you don't want, take the universal cover, put some vertices back in. If L doesn't have this property, you embed L in something like L cross an interval. This will usually have that property. You can embed L as a full subcomplex of some other simplicial complex that has this property, and then you can build XLS as a subcomplex of XNS, where n is this. Okay, I guess I should stop there. Questions?
Could you say something about where your what sort of L's you want to? I mean, you said that they exist.
Yeah, the L I like is comes from the Higman group, but it does. I mean, I'm not using anything out of the Higman group except that it's aspherical and that it's acyclic and two-dimensional. So yeah, because Bestvina and Brady always talk about the two scaling of the Poincare homology sphere. Yeah, the universal cover of that is a three-sphere with 120 balls knocked out. It's not something I want because it's not acyclic. So my L, the fundamental group, has to be infinite. So the L I like is the one coming from the presentation of the Higman group. But I'm not using anything special out of the Higman group except that this presentation 2 complex is a K Higman 1. Okay, so then that's obviously not a simplicial complex. It's made from 5 pentagons. So I guess I haven't told you which way conjugation works. So. It could be that way, yeah. I don't know. That's a sensible way. So I draw 4 pentagons. So I start with 1 vertex, 4 edges and 4 pentagons. I take the first barycentric subdivision. I think this is a delta complex in the sense of Hatcher already. Anyway, it's still not a simplicial complex. But then I take its second barycentric subdivision. So I end up with 240 triangles, 336 edges and 97 vertices, I think. Yeah, that's the sort of L I like. And this L I don't need to do anything fancy with. It has no local cut points anyway. So yeah, this is the sort of L I like.
Another thing I wanted to ask was, you're just passing from L to universal cover, but it seems like you could also pass all kinds of intermediate covers, and there's all kinds of fun games.
Yeah, I sort of make that remark somewhere in the paper. Yeah, I could embed L into another flag complex such that the fundamental group dies a bit. And, I haven't thought of any. I know. The thing is that if you just look at the Stallings example inside free 2 cross free 2. So the Bestvina-Brady group for this, I'm going to take the 4 directed edges to the A, B, C, and D. The Bestvina-Brady group is A, B, C, D, subject to a to the n, b to the n, c to the n, d to the n equals 1 for all n in z. Right, so this group doesn't have very many properties, but one of the things I can say is that by varying the subset that you allow the n's in, you get uncountably many groups like this. But I mean, again, what properties do they have? So, yeah, if you wanted to do it, say, with the square of the generator instead, that would be like putting a to the n, b to the n, c to the n, d to the n squared equals 1 for all n in z, and only putting this one for all n in s. Yeah. Oh yeah, and this is in the case when 0 is an element of S. If 0 is not an element of S, then I want twice as many generators, A, B, C, D, E, F, G, H. And then I've got a cyclic 2 that swaps A and E, B and F, etc. Anyway, yeah. So yeah, you can do, I haven't thought what to do with the proper subgroups of fundamental group yet, but yeah, you can do it.
For the quasi-isometries, what are you using to distinguish the QI class?
Bowditch is length spectrum of a graph, right? So a loop, you make a 2 complex by attaching all the disks to loops of length less than m. If you have a loop of length n that's not null homotopic in that, that's a taut loop. So for any particular graph, its Bowditch length spectrum is the set of lengths of taut loops. And by choosing the L's sort of sparse, the S's sort of sparse, you can make the length spectrums. I mean, it's the same sort of argument as, so Bowditch introduced this to show there are uncountably many quasi-isometry classes of 2 generator groups. And he used small cancellation groups. You can exactly work out the length spectrum for the standard graph. We can't exactly work it out, right? We know that we're putting in a loop of this length. We have a cunning cat0 argument to give a lower bound to say that if we just put in a loop of this length, we don't get anything too short out. But we don't know the spectrum exactly. We just know that if we can say, if we either put this relation in or not, we get something in this range or not. And then we can make this range distinct and big enough from the other, yeah. So yeah, it's Bowditch's length spectrum, but it's slightly more complicated than the original. Yeah, no, sorry, I'm still, yeah, I should have stopped already. The tape's probably run out. But if you have 2 cat0 cube complexes, this is the lemma. If you have 2 cat0 cube complexes and a map from one to the other, and you have 2 points in X that get identified in Y, the distance between the 2 points in X is at least twice the distance to the branch locus. Well, that's sort of obvious, isn't it? Yeah, because the geodesic, you know, otherwise, if you don't go to the branch locus and come back, you've made a closed geodesic loop inside a cat0 space, inside the cat0 space Y. Right, so that's the lemma we use to give a lower bound on the lengths of words that can get killed when we attach a given word. Because attaching the word with n is like doing something at height n in the cat0 cube complex. Oh, except height n in the Morse function sense. That's actually n divided by square root of dimension of something in cat0 metric length. Anyway, sorry, that was too long an answer, but yeah.
Break.
I didn't manage to filibuster through the whole tea break. Oh.
Some of it.
Should we stop?
Yes.
Anybody want to say anything else before we stop? Oh.